So why do we conduct correlational studies? One reason is to examine the relationship between variables as they naturally occur. So things naturally occur. We want to know if they're related. That is a correlational study frequently. So you might look at birth order in feelings of responsibility, for example. Are they related? Those who were born earlier may have a higher feeling or a lower feeling. Who knows? How about GPA and internal locus of control? Is there a relationship between those two things? Do people with lower GPAs have a higher locus of control, or do people with a higher GPA have a lower locus of control, or they both go up? Who knows? Another reason we do these sorts of studies is for practical or ethical considerations. Because of those considerations, we can't do experimental studies where we're actively manipulating the independent variables, so we just measure things how they are and correlate them. So smoking and cancer rates, for example, we're not going to make people smoke, randomly assign them to smoke. We just look at the naturally occurring relationship among those things. Higher amounts of smokings, higher amounts of residual cancers. Income years of education, again, you can't assign people to different income levels or years of education for that matter. And so to measure the relationship between these two things, you just measure them and calculate a correlation. So basically, any of these sort of demographic variables that you can't manipulate, you're just sort of stuck with how they are. Correlation is not a bad idea to use instead. So sometimes you use correlational research because there's no obvious variable that is the independent or dependent variable. You just want to know, hey, are these two things related? That's what number 3 means. So depression and anxiety, which one causes which, who knows? We just want to know, is there a relationship? And there obviously is, because they use the same drugs for the two. There's no obvious IV or DV. You just think that levels of depression, levels of anxiety are correlated. We also use it when we're just sort of exploring a new area of research. We're not really testing hypotheses, so we are doing exploratory research just to see, hey, what's related to this thing of interest? So you might start out by looking at what factors might be worthy of further study just by looking for relationships and moving on. Let's do more thorough studies. So let's talk about scatterplots. So scatterplots are visual ways to show relationships between variables. So here's one of those. We've got country, and in these various countries, and it keeps going beyond 6, by the way, it's just a cutoff. We have male life expectancy in years, female life expectancy in years, and infant mortality rate. And so let's see how these things might be related using a scatterplot. So on the left, we have a plot or scatterplot of male life expectancy on the up and down axis, the y-axis, and female life expectancy on the x-axis, the horizontal one. And you can see that countries that tend to have higher male life expectancy also tend to have higher female life expectancy. The opposite is also true. Countries that have lower male life expectancy tend to have lower female life expectancy. So that's a particular type of correlational relationship called a positive correlation. As one variable is higher, the other one also tends to be higher. So here is the opposite type of relationship. This is infant mortality rate per 100 or 1,000 live births. And here is female life expectancy in years again. And you can see in countries where there is a high level of infant mortality, so here's the highest one, whatever that is, 160 or something, it's associated with the lowest female life expectancy. In countries with the lowest infant mortality rates, we have the highest female life expectancy. So higher this is associated with lower that. That is what we call a negative correlation. That is another type of relationship you can see with scatterplots. So a little bit more on scatterplots now. Let's talk about what they describe. So from scatterplots, they give you a feel for both the strength and direction of relationships between variables. So here are 4 different scatterplots, and I tell you which ones are strong, which ones are weak, So here's your weak, here's your strong. These are positive relationships, and these are negative relationships. So the strength is indicated by how closely the points or dots cluster together. So these ones are stronger because the dots are tighter together than they are over here, right? So when they're more tightly clustered, we call that, it's an indication that there's a stronger correlation or stronger relationship. So the direction is indicated by how the line, if you were to draw a line through these dots, would slope. Would it go up from left to right or down from left to right? Up from left to right or down from left to right? Up indicates positive relationships, like that, and down indicates negative relationships, like that. So let's talk about types of relationships or not between variables. So we have positive, which we just reviewed. So positive relationships, negative relationships, no relationships, and curvilinear relationships. So a little more detail. So let's talk about positives. So in positive relationships, the variables tend to increase and decrease in the same direction. As one goes up, the other goes up. As one goes down, the other goes down. We have two examples over here. This is a stronger relationship than this one is because the dots are more tightly clustered. So as one variable increases, the other also tends to increase. As one variable decreases, the other also tends to decrease. The point here is that they move in the same direction. Okay. So for example, taller people tend to weigh more. As height goes up, weight tends to go up. Students who attend more classes tend to score higher on tests. Higher attendance, higher scores. One goes up, the other one goes up. Higher alcohol use typically increases your risk of falling down. So drinking more, as that goes up, your risk of falling also goes up. As interest in my lectures decreases, so does student wakefulness. So as they are more interesting, student wakefulness also tends to be higher. Now here's some examples of a negative one. So having less money, when your money is lower, it's associated with fewer leisure activity choices. So having less money is associated with lower leisure activity choices, which is totally true, right? Couples who are married longer, so as marriage goes up, they tend to be healthier and happier. Health goes up and happier goes up. So this is multiple positive relationships here. How about another positive example from the real world? Here is a plot of NIH funding in millions of dollars for different disease conditions, and here is an estimate of how much life years, that is years that people would have lived if the disease hadn't existed, are lost as a function of these different diseases. And so as you go out here, you get diseases that are more sort of severe in terms of they kill people younger, they take away more years of life. So you go higher here, you get higher levels of funding. And so what you see is that in general, health issues that have a bigger impact on lives, those out here, tend to be higher on the funding, right? There are a couple oddball exceptions to that, though. For example, there's tuberculosis over here, which is somewhere in the hundreds of millions of dollars, yet really doesn't, do that much in terms of years of life lost. Another example is COPD. So COPD is underfunded, you'd say. It takes a lot of over 1 million life years away from that people would have otherwise had, yet it's not even on the line with the other ones. It is an underestimate. And then at the top of things, we have HIV, AIDS, where it's tremendously funded, $300 million a year. And actually, the amount of life lost isn't commensurate with the funding level. So it's an outlier in the high direction. So let's talk about negative relationships now. Negative relationships are when, as one variables tend to increase, the other one tends to decrease. So they move up and down in opposite directions. So the variables tend to increase and decrease in opposite directions. So what's that mean? Well, as one variable increases, the other tends to decrease, and vice versa. As one variable decreases, the other tends to increase. The point here is that they move in opposite directions. That, again, is sort of the take-home. Negative doesn't mean going down, it means they move in opposite directions. So that's sometimes confusing. Positive means they moved in the same direction. So some examples. Heavier people tend to be shorter. As weight goes up, height tends to go down. I don't know if that's true, but it's an example anyway for didactic purposes. Students who ditch more classes tend to score lower on the tests. As ditching goes up, test scores tend to go down. Higher alcohol consumption tends to worsen driving ability. That is a real one. So as alcohol goes up, driving ability goes down. As a man's comfort in a relationship increases, the probability that he will put down the toilet seat decreases. A funny one. A real one here, employees who report to more managers tend to be less happy. So as the number of managers you report to totally makes sense, goes up. Yeah, you tend to be less happy because there's more people coming down on you. And younger mothers tend to have higher odds of birthing healthy children. What? Think about that. So lower age is younger, right? So lower age mothers, higher odds of healthy children. This is a true negative correlation. Older mothers, conversely, have lower odds of birthing healthy children. So that's the flip side. So a real world example, hopefully vaguely interesting to you guys. What we have here on the up and down axis, the y-axis, is the sepsis mortality rate. So sepsis is a systemic infection, and so it kills a lot of people. Actually, half of everyone who dies in a hospital has sepsis. And these are level of analysis here is a hospital. So we have the hospital sepsis mortality rate on the up and down axis. On the x-axis, we have the percent of the time that the hospital follows proper treatment protocols for treating sepsis. That is, getting fluids in them, getting them on systemic antibiotics, etc. And what you see here is that there's a negative relationship. So higher levels of sepsis mortality are associated with lower levels of compliance. So and this is a real distribution, so the data are messy, right? You can see there's actually dots kind of all over the place, but in general, the relationship is that those who, I'll say it the other way, those who tend to comply better with sepsis care have lower mortality rates from sepsis. Relationship's not very strong. It's negative 0.17, which you guys don't necessarily know what that means yet, so we'll get to that later, but it is a true negative correlation in the real world. All right, so let's talk about no relationship. What's that look like on a scatter plot? Well, it's just dots all over the place with no clear sort of line of things. Generally, this is what they show is the red and blue on the left. Also, the two at the bottom are no correlation, and what they lack is variability in one of the axes. So, and the one on the left at the bottom, there's no real variability in the x-axis, even though there is in the y. In the plot on the right at the bottom, there's plenty of variability in the x-axis and no variability in the y. And when you do that, you end up finding no relationship. We call that restriction of range. So no relationship, it's kind of hard to describe, but basically the variables don't tend to be related to each other. Whether one increases or decreases is totally unrelated to the value on the other variable. Okay, so there's no relationship between them. So as one variable increases, the other does not change predictably. That's probably the simplest way to say it. As one variable decreases, the other one does not change predictably. It's just the opposite way of saying the same thing. No relationship. You can't predict one from the other. Another way to say it. So for example, hair length and intelligence, not related. There's people with long hair and short hair who are both smart and dumb, right? Grades and lifetime number of ice cream cones consumed. Whew, tongue twister. Again, no relationship. There is people with bad grades who eat lots of ice cream, people with bad grades who eat no ice cream, right? So no relationship. Income and number of close friends is a real one. So there are poor people who have lots of close friends, and there are rich people who have lots of close friends. So there's no real relationship across the whole spectrum. Adult IQ and shoe size. Again, there's people with big feet and small feet who are both dumb and smart. Wisdom and ability to talk for extended periods. Absolutely. You've probably run into this in life. There's people who know a lot, who are willing to talk and not willing to talk, and there's people who don't know jack, who also just won't stop talking, or don't, as presumably don't talk either. So no relationship. Number of seashells you have, number of friends, no relationship. Lunar phases of the moon, and numbers of ED, emergency room visits, also not actually related. That is a urban myth. So let's do an example of no relationship. What we have here is data from OkCupid. And on OkCupid, there's two lines shown here. The red line is women seeking men, so it's heterosexual women who are seeking men. And on the up and down axis is the age that those women found most attractive on OkCupid. I guess they swipe left or right. I don't know. I've been married forever. So whatever age they swipe, this is the average age that they swipe and they find that person attractive. And at the bottom, the x-axis is the age of the woman. And as you can see, older women, so out there, say in their 40s, tend to find older men more attractive. Younger women tend to find younger men more attractive. The whole spectrum sort of follows that line pretty darn closely. However, what do you see for men? Men, the average age of a woman that they swipe right on, I guess that's the good direction, doesn't really vary much across the entire age spectrum. So you're never going to look at grandpa the same again after this, but basically, regardless of the man's age, they like 20 to 24-year-olds. So it's the creepiest real-world example of no relationship whatsoever between the man's age and the age of the women they find most attractive, whereas that is a positive relationship between women and the age they find most attractive. So one other type of relationship is what's called a curvilinear relationship. So in curvilinear relationships, the variables are related, but it's not by a constant ratio or in a single direction, which is a really complicated way of saying a straight line doesn't do a good job of representing the relationship between the variables. So in a linear relationship, the relationship is well represented by a straight line. So these two over here, even though they're lines, they're curvy, right? So these are curvilinear relationships in the picture. So as one variable increases in a curvilinear relationship, the other one changes in multiple directions, or the change happens at a faster or slower rate. I mean, a straight line doesn't do a good job of representing these curvilinear relationships. So what am I talking about here? So cheerfulness and customer satisfaction. So higher satisfaction up to a point with cheerfulness, but if people are too cheerful, it starts dropping back down again. It becomes annoying to people. So that's this top one on the right. You can see that relationship. A little bit of cheerfulness is good up to a point, and then they're like, will you stop being so happy? And it starts dropping again. Advertising and cleaning products using fear of germs. So again, a little bit works, right? If you tell people, there's germs on things or whatever, but if you just really try to scare them, people react in the opposite way and do not buy your product. So you don't want to go beyond sort of a sweet spot in advertising using fear. Yerkes-Dodson is probably the classic example of a curvilinear relationship. It's that one up top again, where it's a relationship between anxiety and test performance. So if you're not a little bit anxious or a little bit sort of worked up about things, you tend to perform pretty poorly. A medium level of performance actually, or medium level of anxiety actually does increase your performance up to a point. But if you're too anxious, you tend to do poorly again. So a little bit of anxiety is not enough. Medium's about right. High anxiety isn't enough. So it's kind of like the Goldilocks and the Three Bears. Another one that's like the one on the bottom is lottery ticket sales and prize money. So it's an exponential relationship. You can see it looks sort of straight, but it's not. It's actually curvy. And what happens is as the pot goes up for the lottery, the rate that people buy tickets increases exponentially, right? When it gets into the billions or whatever, people are buying tickets like crazy. And so it looks like that one at the bottom, which is not well represented by a straight line. So a real-world curvilinear example is the relationship between ASDR per 1,000 person years, and males and females. So what is ASDR? That is basically risk of death. Okay, all cause risk of death. So I don't remember what S stands for, death risk. But it's basically the rate that people die. So it turns out that if you make it through your first year of life, which is extremely risky for dying, your risk then becomes very, very low. Okay, and it actually drops a little from 1 to 4 to 5 to 9. It then remains pretty darn low for, I don't know, from age like 1 to somewhere out here. You still got a really low risk of dying. But then when you get to your 60s, it starts increasing exponentially, and your risk of dying increases dramatically. So this is curvilinear because you have a high risk at the low end, high risk at the upper end, and sort of flat or slowly, almost linear in between. So a straight line does not do a good job of representing this relationship at all, and so that's why it's curvilinear. So the Pearson product, so that's scatter plots, and that's one way of looking at relationships between variables. Another way is to do it mathematically. And again, in this class, SPSS does the stats for you, so this shouldn't be too scary. So it's called the Pearson product moment correlation coefficient. It's also called Pearson's R. I'll tend to just call it correlation or R or something like that. And it is the most common mathematical way of summarizing the strength and direction of linear, underlined, relationships between two variables. So from this one number, you get the strength and direction, kind of like we got from the scatter plots, but it's a number, so there's less guessing here. But it's only for linear relationships. So it is typically used for ordinal or interval or higher scalar measurement, that is continuous variables. It can be used if you've got a nominal variable that's only dichotomous. That means it only has two levels. So for example, yes, no, male, female, employed, not employed, you could use the correlation coefficient for finding relationships, the strength and direction, with nominal variables that are scaled like that, and other nominal variables that are scaled like that, or those nominal variables with two levels and continuous ones. So it cannot be used if you got a nominal variable that's got more than two levels, like period. If you got something, religion, hair color, you can't use it. You've got more than two levels. So for example, here we go. There's examples. Birth, religion, ethnicity, birth state. These are all things you can't use correlation coefficients with because they're nominal variables with multiple levels beyond two. All right, so the Pearson product moment correlation coefficient continued. It's a number. It ranges between -1 and +1. SPSS is going to calculate it for you. The strength is indicated by the absolute value of the coefficient. So ignoring the sign, how close is it to 1? Ones that are closer to 1 indicate a stronger relationship between the variables. Closer to 0 is a weaker relationship between the variables. The direction of the relationship is indicated by the sign. So if it's got a negative, or just go through it, if it's got a positive or no sign, which is what SPSS does, you have a positive relationship. A negative or negative sign is a negative relationship. So these are those same correlations we were looking at in the scatter plot. So they can only be used with linear relationships, meaning relationships, again, that are well represented by a straight line. So before you calculate these, you should always look at a scatter plot of the two variables. So that's why we did scatter plots first. So you look at the scatter plot before you calculate your Pearson R. Why? Well, it only does a good job of representing linear relationships. So you want to make sure the relationship between the variables is linear before you calculate this. If you use it for nonlinear, that is curvilinear relationships, it will underestimate the true relationship between the variables. It does not give you a good estimate of that. So some examples. Here are 3 Pearson correlation coefficients with their corresponding scatter plots. And again, we said as the dots are closer clustered together, it's a stronger relationship, and this is sort of mathematically what that would look like. An R of 0.3, the dots are pretty far from the line in general, even though it is positive. 0.7, they're closer. and an R of 1.0, they're perfectly on a line. You can perfectly predict an X value from a Y value, for example. Here are 3 negative correlations. Same thing. The sign is different. They're all negative, so they go down from left to right instead of up from left to right. And the stronger the correlation coefficient, the closer the dots are clustered to a straight line. So the strength of the correlation coefficient, that is R, increases as the points cluster closer to the line, and the direction is indicated by the sign of the coefficient. So here's a real-world example. This is on the up and down axis, the rate-adjusted number of Nobel laureates per 10 million population. So in normal person language, it's how many Nobel laureates you get per 10 million population. On the x-axis, the horizontal one is chocolate consumptions in kilograms per year. What kind of relationship do you see in this figure? Kind of looks like, in general, countries that tend to have higher chocolate consumption tend to have more Nobel laureates per population. And indeed, the correlation coefficient is in there. It's 0.79, and it's statistically significant. There's a relatively strong correlation. This is one of those goofy ones between chocolate consumption and Nobel laureate rates. All right, so we test hypotheses with correlation coefficients, and you can choose whether you want to do a directional or a non-directional hypothesis. So let's talk about the non-directional ones first. They're a little easier. So they're always written as how R is related to 0. So 0 meaning no relationship between the variables, and you write 2 exclusive hypotheses. The null hypothesis, or HO, always indicates no relationship. And sometimes it's also the relationship is not in the predicted direction. So the null always has no relationship in it, though, as a possibility. Sometimes it also has the opposite of what is predicted. Like if you're predicting a positive in your study, a negative would be in the null hypothesis. You have to disprove that in order to support that there's a positive. The alternative hypothesis, which I usually write first, is or the H1 is what relationship you predict will be found between 2 variables. So the alternative comes from the research hypothesis, what you predict you're going to find. And so the way I do this, and I'm going to teach you to do it, is write the alternative first. What is it the researcher is predicting they'll find? And then everything else goes in the null, right? So it's a great way to do this. So let's do it. Oh, sorry. So non-directional two-tailed hypotheses, another way of saying those. This is when you're not predicting specifically a positive or negative relationship. All you're saying here is, I think there's going to be some sort of relationship between X and Y. They will be related. So it's pretty non-committal. You're correct in either direction, right? If you just say, I think these 2 things are going to be related, and you find a positive relationship, you're right. If you find a negative relationship, you're also right. The only case you're wrong is if you find no relationship. What does no relationship mean in terms of a correlation coefficient? Well, that would mean an R equal to 0. So let's say your research hypothesis was exam scores are related to student age. That is non-directional. Why? Because you're not saying, I think older students will do better. You're not saying, I think younger students will do better. You're just saying there's going to be some sort of relationship. You are correct if you find a negative or a positive correlation. So there's our null. There's our alternative. I'm going to do our alternative first, or H1. So between R and 0 for the H1, how do I say I think that there's going to be some sort of relationship? Well, the way you do it is you say R is not going to be equal to 0. What does that mean? Well, what does R equal to 0 mean? R equals to 0 tells you there is no relationship between the variables, right? So the closer you get to 1, the stronger. The closer you get to 0, the weaker. So if for your alternative, your H1, you say R will not be equal to 0, you're saying there's going to be some sort of relationship. So your null hypothesis is going to be, where are you wrong? where would you be wrong in your hypothesis that there's some sort of relationship? You would be wrong if there really was no relationship. So what's going to go between r and 0 on the null? Equal to 0. That's the one case where you're wrong. If you get an r that's 0, yeah, there's no relationship. You're wrong. Anything else, not 0, positive or negative, your hypothesis is supported. So that's how you do two-tailed ones. And they're always written exactly the same. Always. All right, so directional hypothesis is where you pick a direction. You say, I think there's going to be a positive relationship, or I think there's going to be a negative relationship, but only one of those two, okay? That's directional. So there is a positive or negative relationship between x and y. It is committal, so you are correct only if the direction you predict comes up. So first of all, it's got to be a correlation. It has to be not 0, just like with the two-tailed. And secondly, it has to be in the direction you predict. Otherwise, you're wrong, right? So there are two variations, but only two variations of how you write these directional hypotheses. So, for example, a positive relationship. You say that higher values of x are going to be associated with higher values of y. So x goes up, y tends to go up. So real world, having more sexual partners is associated with higher STD rates. Probably true. There's our null, there's our alternative. So for our alternative, our H1, we need to write having more sexual partners is associated with higher STD rates. So R is the correlation coefficient. 0 means no relationship. If we're predicting that more sexual partners is associated with higher STD rates, we're predicting that R is going to be positive, right? A positive non-zero number. So we are predicting that R will be greater than 0. Your null hypothesis then is all other possibilities. Where are you wrong? Well, you would be wrong if you found that R was less than 0. That is, having more sexual partners is associated with lower STD rates. That'd be a negative relationship, R less than 0. You would also be wrong in your hypothesis if there was no relationship whatsoever. So it's R less than or equal to 0 is your null. Again, R greater than 0 is a positive relationship. That goes in your H1. Everything else where you're wrong goes in your null, your HO. So negative relationships are the flip of that. You're saying this is where they move in opposite directions. So higher levels of X are associated with lower levels of Y. So increased condom use, as condom use goes up, STD rates go down. Probably true again, right? As one goes up, the other one tends to go down. Our null and our alternative. So R and 0 in your H1 there, how do you say, I think I'm going to find a negative relationship? Well, what will R be if it's a negative relationship? It will be not 0, and it's going to be something less than 0, right? Because 0 means no relationship, less than 0 means negative. So you're predicting that R is going to be a value that is less than 0. So where are you wrong? Again, you're going to be wrong if you find a positive relationship. If you find that increased condom use is associated with higher STDs, you're wrong. So that's going in your null. Where else are you wrong? Well, you're wrong if you don't find any relationship whatsoever. So how do we write that? Well, you're wrong if R is greater than or equal to 0. Greater than 0 would mean positive. Equal to 0 would mean no relationship whatsoever. So those are the three different ways to write your correlation coefficients. And I know you're probably shaking your head now, but we're going to do plenty of examples of these, so you will get this down, I promise you. So let's talk about hypothesis testing for correlations some more. So SPSS calculates not only the correlation coefficient for you, but it calculates something called a p-value, or it calls it a sig value. And what is this p-value? Well, the p-value tells you the probability, that's why it's a p, that you could get the correlation coefficient by chance if no relationship actually exists between the variables. That is, the null hypothesis is true. So p tells you the probability, the correlation coefficient you got is just chance, not real, okay? So, for example, a p-value of 0.32 indicates that, 32% of the time you could have found a correlation coefficient of this strength or even higher just by chance, even if the null was true. Okay, it's a very almost a 1 in 3 chance you could find that even when a relationship does not exist. So conventionally, particularly in psychology, researchers are willing to conclude that a correlation is real if it would have occurred less than 5% of the time just by chance. So if the p-value you get is less than 5, it means, yeah, it could have happened by chance, but it's pretty rare, right? It's less than 5% of the time you would have got a relationship of that size or bigger just by chance. Well, that's that alpha level thing. So there's an alpha level that we use to interpret the statistical significance of our stats. The alpha level is the amount of chance you're willing to accept, and it is conventionally set at 0.05. That is a 5% chance that it is not a real relationship. 5% chance of being wrong. So an alpha less than 0.05 means that the probability that a correlation is the result of just chance, just happened to get this relationship, it's not real, is less than 5%. So to determine if a correlation coefficient is real, we're going to compare sig, that SPSS calculates, to 0.05. We're going to follow the following rules to determine if it's real. So to fully reject a two-tail hypothesis, there's only one requirement. Okay, two-tail again was some sort of relationship was what you were predicting, not positive, not negative. So all you got to show is there's some sort of relationship. So the only requirement to establish that there is some sort of relationship between your variables is that your sig, and it calls it two-tailed sig, is less than 0.05. If your sig is less than 0.05, that tells you your correlation is statistically significant. It's real. It's not just a chance finding. So two-tailed hypotheses, remember there's two parts of the null, so we have to reject two parts of the null. First of all, it's the same as number one, the sig, but it's called a one-tailed sig. It has to be less than 0.05. So what's that mean? The correlation has to be statistically significant. It's not just a chance finding, less than 5 times in 100. You would have gotten a correlation that big just by chance. So you establish, number one, yeah, there is a relationship between the variables. It's not just chance. The second part of this, you have to show that the relationship is in the direction you predicted. So the correlation coefficient sign is in the hypothesized direction. It's real and it's in the direction that you predicted, positive or negative. So there's something called a measure of effect size for correlations. The measure of effect size for correlations allows you to interpret the relationship between x and y, the two variables, in terms of variance explained or variance you can predict in one from the other. And it's r squared. You just take the r and you multiply it by itself, or use the square key on your phone. So it is a measure of effect size that's called the coefficient of determination, or r squared. This is coefficient of determination is the fancy name for r squared. I just call it r squared. You just square the correlation coefficient. That's all you do, and it gives you this percent of variance in one variable explained by the other, or predicted by the other. So, okay, proportion, whatever. So it tells you the proportion of variability in one variable that can be accounted for, explained, or predicted by the other, and vice versa. It's bidirectional. So if you scooch the decimal over 2 spots, you've got a percent. Big whoop. So r square is important because it tells you how meaningful the relationship between two variables is. So you can have a statistically significant correlation that's really small, and so therefore you don't really care. So if it is a big relationship or a small relationship, this is what you get from the r squared coefficient. So for example, if r is equal to 0.4, then your r squared, that is 0.4 times 0.4 squared, is 16. That's 16% of the variability, and one variable, okay, times 100. 16% of the variability in one variable can be predicted by the other. It's a decent relationship. What if r is equal to 0.2? Well, r squared is equal to 0.04. Only 4% of the variability in one variable can be predicted by the other. So the top one's a much stronger relationship than the bottom one. So what in case that's too abstract for you, I have some Venn diagram examples here of different correlation effect sizes where we square r. So if r is equal to 0, then r squared is also equal to 0. There's 0% overlap between the variables. So like using the internet and having privacy. There's no, Those two things don't overlap whatsoever. There's 0% relationship. So if r is 0.25, we square that, we get 0.06, 6% overlap. So there's a 6% of the variability in one variable can be predicted by the other. In this example, liking gory movies and liking musicals don't have a whole lot of overlap. An even bigger correlation, 0.5, is 25% of the variance if you do the math. So we got George Washington and Sir Mix-a-Lot. They have about 25% overlapping variability, and they both had an inability to lie. Finally, what if we have a perfect positive correlation? R is equal to 1. Well, we have perfect overlap. 1 squared times 100 is 100%. You have perfect overlap. Blue plus red is purple. Hopefully that helps clarify this. So APA, I think it's the first example of this. One way to teach APA format is make you buy the manual and tell you to read it and write your papers like that. And I think that's awful. So the way we do it in this class is I give you examples. I tell you some of the basics of how to write things up in APA, or American Psychological Association format. And then I give you example papers that you kind of type over and copy in order to write up your APA results. So it's using a template, and there is no, you don't have to worry about plagiarism. I give them to you for the express purpose of you to type over, change variable names, etc. Okay, so make sure you do that. Do not write things from scratch in this class for APA. But they have all these rules. So kind of like the rounding rule we talked about during one of the SPSS assignments. Usually it's 2 decimal points beyond the unit of measurement. So most things get rounded to 2 decimal places in APA. They got rules for everything. So, and you're not going to learn them all, and you're sure as heck not going to remember them all. I do this for a living, and I don't remember them all either. So I will give you what's called the general format, and you will then adopt that general format and fill in the stuff for your APA write-ups. So here is a correlation right here between age and assertiveness. The correlation coefficient is 0.314. This right here with the yellow in it is the APA way of writing up your correlation coefficients. You need to fill in something called DF, degrees of freedom. That number to 2 decimal places is the correlation coefficient rounded to 2 decimals. Then you have to pick a less than or greater than sign to go between P and your alpha level of 0.05. And then finally, you have to square the R value and report that as your R squared. So let's do this. So first of all, DF, the degrees of freedom thing that goes in the parentheses right after R, is just n minus 2. N's in the table. You can see it's 59 for this. 59 minus 2 is 57. You will round the correlation coefficient and R squared to 2 decimals because APA demands it, and only report the sign of the coefficient if it's negative. So you don't put a plus on the positives, right? You just put a negative on the negatives. So there we go, negative 0.49, but you wouldn't put plus sign 0.49. So these results in APA format look like this. An R of 57, that is 59 minus 2 is 57, is equal to 0.31. That's our correlation coefficient. 0.314 rounded to 2 decimals is 0.31. Is it statistically significant? Well, let's see. There's our sig value, one tail. Apparently this is a one-tailed hypothesis. Is 0.008 less than 0.05 or greater than 0.05? Well, it's less than 0.05. Hence, P less than 0.05. And finally, R squared is 0.314 times 0.314, which is 0.0985. We're going to round that to 2 decimals. That's 0.10. 10% of the variability in assertiveness is predicted by age. That is, unfortunately, there's rules for all the ways we have to write these up for APA, and I just we just gotta work through it and get it done. So testing a correlation hypothesis. Let's do this using a 2-tailed example. You're going to do this on your homework and a couple of assignments in class. So let's go ahead and give this a shot. This is going to be a 2-tailed hypothesis. So for example, I think sex will be associated with emotional intelligence levels. So I'm not saying I think males will be more emotionally intelligent, females will be more emotionally intelligent. I'm just saying there's going to be a relationship, right? between sex and emotional intelligence. That's why this is a two-tailed hypothesis. Here's what the scatter plot looks like. And it's crazy because sex is a nominal variable. It's got two levels, 1 and 2, right? Sex is dichotomous, so we can use it in correlation. And you have to know how it was coded to understand or interpret this scatter plot. Like what's a 1 and what's a 2 on that up and down axis? How do we know? Well, it turns out 1 was male and 2 was female. Emotional intelligence is on the x-axis. It's continuous, so we don't have any sort of funky nominal coding scheme for that. Okay. So is the hypothesis up above, sex will be associated with emotional intelligence, is that one-tailed or two-tailed? It is two-tailed. We're just saying there's going to be some sort of relationship between sex and emotional intelligence. So it's two-tailed. So how do we write two-tailed hypotheses? Well, remember H1, your alternative, is always what you think or what the research hypothesis is for a study. Sex will be associated with emotional intelligence. So thinking about R, the correlation coefficient, and 0, when is it correct that sex is associated with emotional intelligence? Well, it's correct when R is not equal to 0. That's it, right? If R is equal to 0, that's the only case where you're wrong. So guess what's in your null? R equals 0. So two-tailed correlations are always written like this. Your null hypothesis is not equal to 0. Your alternative, or HO, is R is equal to 0, because that's the only case where you're wrong. So do the variables appear related in the hypothesized direction? Well, there is no hypothesized direction, so done. Maybe, I don't even know how to answer that. Sure, because we didn't pick one. All right, so same relationship, sex associated with emotional intelligence. Here's correlation coefficient. This is the output from SPSS. So we have a correlation coefficient of 0.015, sig is 0.910, and n is 60. Here's our decision rule. Sig's got to be less than 0.05 for us to say this is a real relationship. So is this correlation statistically significant? Is 0.910 less than 0.05? No, it's not. So this relationship, or this correlation between sex and emotional intelligence, there's a 91% chance it's not real. That's what the 0.91 means. Okay, there's a really big chance. This is just garbage correlation. Look how small it is too. It's very close to 0. So is it in the hypothesized direction? Again, there is no hypothesized direction, so that's dumb. Are you able to fully reject the null? Well, what's the one thing that has to be true for you to fully reject a null of a two-tailed hypothesis in correlation? Well, it's got to be sig. It's got to be, the sig has to be less than 0.05, right? It's got to be statistically significant. It's not, so no. Why? Because sig's greater than 0.05. There's no relationship between sex and emotional intelligence. So how would we write this up in APA format? That's what it would be. And R58 is equal to 0.02. P was greater than 0.05. That is, the sig was greater than 0.05. And if you square 0.02, you get basically 0, 0. All right, so how about a positive correlation example? How about older people tend to be more assertive than younger people? So as age goes up, assertiveness tends to go up. There is age and assertiveness in a scatter plot. Does that look like it might be a positive relationship? Kinda. It's not great, right? Like the dots are pretty far from the line in some spots. Our variables are age, that's continuous on the up and down axis. Assertiveness is continuous, that's on the x-axis, the horizontal axis. This is two or one-tailed hypothesis. Is it non-directional or directional? Well, in this case, the researcher is predicting specifically, not that there's just going to be some relationship between age and assertiveness. No, they said older people are going to be more assertive. They've picked a direction, right? As age goes up, assertiveness goes up. This is a one-tailed hypothesis. So how do we write the hypotheses in numeric form? Well, remember your H1 is your research hypothesis. This is where you state what the researcher expects to find. This researcher expects to find a positive relationship. As age goes up, assertiveness tends to go up. That means that R is going to be something greater than 0, right? It's not going to be 0. It's not going to be less than 0. You're wrong. It's going to be R. You're predicting that R will be greater than 0. That means it's if it's greater than 0, it's positive, right? If it's 0, it's non-existent, and if it's less than 0, it's negative. So if we're predicting that r will be greater than 0, positive, where are we wrong? Well, we're wrong if we find a negative relationship or if we find no relationship. So r less than or equal to 0, that's our null because that's where we're wrong. So does this kind of look like a positive correlation? Yeah, it does. It appears to be positive. So let's actually test it. Same hypothesis. Here's our correlation coefficient, 0.314. Sig is 0.008 and n is 59. So our decision rule, remember there's two parts. Okay, part number one is sig has to be less than 0.05. That's thing number one that has to be true to reject a one-tailed hypothesis. Either one, by the way. Also, the sign of the coefficient has to be in the predicted direction. What did they predict? Positive. So it has to be, sig has to be less than 0.05, and it needs to be a positive relationship for us to reject the null hypothesis. So first of all, is it statistically significant? So we compare sig to alpha 0.05, 0.008 is less than 0.05. So yeah, this is a real relationship. There is a real relationship between age and assertiveness. Is it in the hypothesized direction? That is it positive? Well, note that there's no negative on the front of it. So yes, it's real and it's in the right direction. That's what we've established. Are we able to fully reject the null? That is, are both parts above it true? It's significant and it's in the right direction? Yes, it is. Okay, they predicted a positive relationship. We found a real positive relationship. APA format is there. R of 57 is equal to 0.31 rounded. P was less than 0.05. That is 0.008 was less than 0.05. And if you square 0.31, you get something that rounds to 0.10, or 10% of the variability in assertiveness can be predicted by age. All right, how about a negative one? Negative correlation. So from that example earlier, sepsis case mortality will be lower in hospitals that comply more consistently with appropriate sepsis care practices. So it's kind of easier to say the other way. As compliance goes up, death rate goes down, right? But we're saying as death rate goes down, compliance goes up. Probably the other way. So here is that correlation from earlier, and you can see that it does slope down from left to right, which is consistent with the correlation. So what are our variables? Sepsis case mortality on the y-axis, that's continuous. Treatment compliance ranges from 0 to 100, that's on the x-axis. Is this a one or two-tailed hypothesis? So to answer that question, you have to say, am I right, or is the researcher right, if I find any correlation or just one, right? If the answer is just one type of correlation, you got a one-tailed hypothesis. Okay? If either type of correlation, positive or negative, you'd be right, that's two-tailed. So this is a one-tailed hypothesis, right? They're predicting a negative relationship. As one goes up, the other tends to go down. So how do we write these? Well, for our H1 again, we have to write what we're predicting we'll find. So we're not predicting we're going to find a positive relationship. We're not predicting no relationship. We're predicting a negative relationship. So we're predicting that R will be less than 0. It's not going to be 0, it's not going to be positive, it's going to be less than 0. What's less than 0? Negative things, right? So where are we wrong? We're wrong if we find no relationship at all. That is, it's not statistically significant. Or we find a positive relationship. We'd be wrong, right? It could be real and positive, but we'd be wrong. So greater than or equal to is our null hypothesis. Those are the two cases, no relationship or a positive relationship, where our research hypothesis, as expressed in our H1, would be wrong. So does it look like there's a negative relationship? Kinda, right? It's not, there's kind of, it does slope down from left to right. So again, here's our correlation coefficient for sepsis mortality and sepsis compliance. It's negative 0.170, sig is 0.002, and n is huge. Hospitals, 273. Our decision rule is a one-tailed hypothesis, so two things have to be true. Sig has to be less than 0.05. The coefficient has to be in the predicted direction, which is negative correlation. So is it statistically significant? Is 0.002 less than 0.05? Yeah, sure is. So this is a real relationship between sepsis compliance and sepsis mortality. Is it negative? Is it in the hypothesized direction? Look at the signs. Negative 0.17. You bet. Yep, it is. So are both things true? That is, it's real and it's in the right direction. Yes, right. It's significant and the sign is negative, as predicted. How do we write this one up? Note this negative is on there. It's an R of 273 minus 2 is 271. That's your DF. It's equal to negative 0.17. P was less than 0.05, and if you square negative 0.17, you get about 3.03, 3%. And the variability in sepsis mortality is predicted by whether they comply with the sepsis protocols. And again, the R squared is a measure of effect size, and notice how little it is. 3% is not big, right? That's a tiny, not a very meaningful relationship, but it's significant because there's 273 hospitals. So this is an example where we found a significant relationship, but it's, most of why people die of sepsis, the rest of that 97%, has nothing to do with whether they treated them according to the protocol. It's age, comorbidities, anyway, you guys don't care. All right, moving on. So just some follow-up, some final things about causal inference. It is like a meme, basically, that your stats professor is going to tell you correlation is not the same as causation. There's causal ambiguity in correlational studies, meaning just because two things are related, you can't say one caused the other, like ever. Just don't, okay? And I'm going to try to trick you. It doesn't matter how strongly related they are, you can't infer causality. This is kind of funny. Someone did a pumpkin. Some stat professor did a pumpkin inferring causation from correlation for Halloween. All right. So correlation does not imply causation. No matter how strongly the variables are correlated, you cannot infer one caused the other. So, for example, which causes which? A strong positive relationship exists between committing sexually aggressive acts and viewing violent pornography. It's very tempting to say, viewing the violent pornography makes you more likely to be sexually aggressive, but you can't do that, make that conclusion based on a correlational study. They could be not causally related at all. Maybe it's, sociopaths are more likely to be sexually aggressive and more likely to enjoy violent pornography. So there's no causal relationship between watching the pornography and sexually aggressive acts. They appear related because they're related to how much of a sociopath you are, right? Hopefully that makes sense. How about self-esteem and motivation to work? They have a positive relationship. People have higher self-esteem, tend to want to work more. Does low self-esteem cause people to not want to work? Does not wanting to work result in low self-esteem? Who knows? It could be circular. Like, we have no idea, or it could be not causal at all. It could be related to some third variable, right? So again, you cannot infer causation no matter how strongly. If the correlation is perfect, you cannot infer causation in a correlational study. All right, / end of rant. There's something called the third variable confound you run into in correlational studies, and this is one of the examples we just saw with sociopaths, for example. It's when two variables share a common relationship with some third variable. So they appear to be related, but really it's because they're both related to this third thing, okay? Like the violent, aggressive sexual acts and viewing pornography. Both are associated with being more of a sociopath. So they look related, but really they're not. That's called the third variable confound. So these third variables can explain the relationship that you find, the correlation between the two variables. We sometimes call them confounding variables or confounders. So for example, the number of fire trucks that respond to a fire and the severity of damage, they're positively correlated, right? More fire trucks go to a fire, damage in the fire tends to be higher. Why? Well, it's because they're both related to the severity of the fire, not related to each other, right? Another goofy example is shark attacks and ice cream sales. Totally, strongly, positively related. It's not linear in this picture, I agree. But for didactic purposes, just let me keep going. So when shark attacks are high, ice cream sales are high. So would you therefore not want to sell ice cream so that people don't get attacked by sharks? No, it's obviously ridiculous, right? So there's no causal relationship between these variables. What is the third variable they're both related to? Warmer temperature. Okay, as temperature goes up, shark attacks go up, and ice cream sales go up. So it makes those two things appear related when they're really not. I mean, they're related. It's not causally related. Shoe size and reading comprehension also positively related across the entire age spectrum. Why? Age. People with very tiny feet are not very good readers. They're kids, they're babies, right? And as you get older, tend to be a better reader. All right. So there's also reciprocal causation, another reason why you don't want to infer causality in correlational studies. This is when both variables cause each other. You can't tell that from a correlational study. This is just another sort of caveat. Again, don't infer causation. So for example, drinking alcohol and depression, strongly positively related, right? So people who drink more alcohol tend to be more depressed, right? But check it out. Drinking alcohol is a depressant, leads to more depression. More depression, well, you compensate by drinking more alcohol. And it just goes in the circle. We call that reciprocal circular causation. So sometimes people are tempted, note may is italicized, to draw causal conclusions from correlational studies because one variable temporally or in time always occurs before the other. So what am I talking about? So we know, for example, that people who grow up in households where they're abused as children are more likely to be abusers as adults, right? This is also, I think, was my example of particular causality, probabilistic causality. Well, people are always children before they're adults, right? So you could never be an adult abuser or abused as a child because you were an adult abuser. That doesn't make sense, right? It would always have to be, if there's a causal relationship, it would have to be being abused as a child leads to increased probability of being an abuser as an adult. But you still got the problem of the third variable. Both variables, both being abused and being an abuser, are related to third factors, multiple ones like stress and poverty and those sorts of things. So again, another reason, even though it's temporal ordering, so it seems like you can infer causality, don't do it. Okay, do not do it in correlational studies. So factors that affect correlation coefficients. One is the linearity of the relationship. So again, just to reiterate, R indicates the strength and direction of linear. Linear was underlined earlier. Relationships between variables. R will underestimate the relationship if it's curvilinear. So we said that earlier. So that is one factor that affects correlation coefficient values is a relationship linear? If it's not, it will underestimate, the number will underestimate the true relationship. It's the wrong way to do it. So you should always make a scatter plot of the variables to ensure the relationship is linear before you calculate R. Second thing is restriction of range. So restriction of range is if you restrict, you don't look at the full range of values for one or both variables. So what that does is it results in a correlation coefficient that again inaccurately estimates the true relationship between the variables. So what the heck am I talking about? Height and basketball ability. So if you looked at the relationship between height and basketball ability among NBA players, think about it. They're all really good at basketball and they're all really tall. If you've ever been around NBA players, like even the short ones are taller than you most of the time. So you wouldn't find a very strong relationship. Height and basketball ability are not strongly related. Even the little point guards are really good, right? Among NBA players. However, if you look at basketball ability and height in the general population, that is everyday people, strong positive relationship. Taller people tend to be better at basketball. So you restrict the range when you do it just among NBA players. You got mostly tall people, mostly really good at NBA at basketball. You will underestimate the relationship in that case. Third thing is sample size. So when you got a smaller relationship, it takes more people in your sample in order to detect that relationship, right? To say it's real and not just chance. So larger samples give you more what we call statistical power. So sample size is important if you're looking at small relationships. You need a big sample size. Almost done, y'all. So finally, this is your first APA write-up this week. There is an example template for writing up your APA assignment. It's a one-pager. It's real simple. So it's your first one. You'll write up hypothesis 4 on the SPSS assignment using the template that's also available. And you have to put a scatter plot in your APA write-up. And the one that comes from SPSS looks like this. And not only does APA have rules about like how to present a correlation coefficient and how to round things, they have tons of rules about graphs and tables. So you have to make the thing on the left look like the thing on the right. The one on the right is APA compliant. So what did we do? Well, we extended both axes so they start at 0. So note on the left they start at 2 and 30. They both have to start at 0. You have to use real words, which in this case it was for the X and Y axis titles. Got to get rid of the grid lines, and always, always, always put that linear line in there. Have the SPSS calculate that line so you can tell what's going on, because otherwise, like, we're just not really good at this. Let SPSS help you. It's called putting in the line of best fit, that straight line in there. It'll make it for you. Put it in there at the right sloping up, like this, kind of like a positive correlation. Make sure you do that. So finally, there is an assignment this week, just not an SPSS one, just a normal assignment. It's 2 of them actually, where you are looking at correlation coefficients and you need more experience. It's kind of like the IVDV and scales of measurement, but not as crazy. You need to know how to do this hypothesis testing thing, how to write hypotheses and interpret them. So there's something called the correlation significance testing review. It's a big old correlation matrix between various hospital things and how they're related. So note that correlation matrices, you only have to look at one side of the diagonal. So top or bottom, I recommend doing the bottom. It's easier to read. And what you have there is the correlation with each variable and each other variable. It repeats itself above and below the diagonal, so you only have to look at 1/2. So I actually recommend sort of crossing off 1/2, so you don't get, until you get good at this. So that's what the blue triangle is here. So it turns out that interpreting the statistical significance of hypotheses, period, is so important in this class. It's one of the top most important things that I have to teach you. So there are 2 assignments this week where you review how to write hypotheses and how to interpret them. So good luck on your assignments. Post any questions you have in the discussion, and I will be back soon with another lecture.